Let's begin with example 1.4. On the real line R, define a topology whose open sets are the empty set, and every set in R with a finite complement. We call this topology the finite complement topology on R, and denoted by R sub Fc. Okay. So here's the idea. An open set in this topology would be what I've attempted to color in here. Basically the entire real line missing just a finite number of points. Okay, so all these open sets are really big, except of course for the empty set, which is also thrown in there. All right, now here's another definition. 1.18. A topological space X is Hausdorff, note the two F's there, if for every pair of distinct points X and Y in the set X, there exist disjoint neighborhoods U and V of X and Y respectively. Okay. So that means that given any 2 points X and Y, you can find some open set U containing X and some open set V containing Y, such that these two sets are disjoint, meaning that they don't overlap. Their intersection is empty. All right. And what we want to do in exercise 1.36 is to show that the real numbers in this finite complement topology is not Hausdorff. Okay. Most of the topological spaces we work with are going to be Hausdorff. It's a nice property to have, but some of them are not, so this one's not. All right, so to show this not Hausdorff, we just have to show that there's some pair of distinct points which do not have disjoint neighborhoods. All right. So let's just take the points 0 and 1. Those should do. Actually, any two will do here. And suppose that we have any two neighborhoods of those 2 points. So suppose U and V are any two neighborhoods of 0 and 1, respectively. Okay, so 0 is in U and 1 is in V. And I should say that these are neighborhoods in this finite complement topology, right? Okay. Well then, what do U and V look like? They're open sets in this topology, and we know that open sets are complements of finite sets, so it has to be R minus some finite set consisting of points, let's call them x1 through xn. Okay. And well, similarly, V is R minus some other finite set of real numbers, maybe y1 to ym. I can't say n again because it may be a different sized set than U. I mean, it may be missing a different number of points than U was. And now I want to show that no matter which two neighborhoods you pick, the intersection is never empty, right? So they're never disjoint. So we can say what the intersection is, actually. Right? U intersect V. Well, U is missing these points, and V is missing these points. So if you take the intersection of these two sets, it's just going to be R minus all the x's and all the y's. Okay. So let's say x1 to xn and y1 to ym. Okay. And it's possible that there's some overlap between the x's and the y's, but that's okay. If you list a number twice inside of a set, that just means it's in there. You just ignore the redundancy. All right. Good. All right, well, and then let me just keep going here. That's not equal. How do I do not equal? There we go. It's an infinite set R minus a finite number of points, right? So it's not empty. It's not the empty set. Okay. Which means that U and V are not disjoint. Okay, so you take any pair of neighborhoods of 0 and 1, they're never disjoint, and therefore R is not Hausdorff in the finite complement topology.